Welcome back, Algebra 2 students. We're going to have a lesson today on ellipses and circles. This is Mr. Bean, and we got to be prepared because today's lesson is actually two separate lessons combined into one. So let's get our thinking caps on and get moving. The first part of our lesson is to recognize what in the world is an ellipse. Now, a circle, if you remember, it just got a radius. Anywhere from the center, the radius is going to be the same no matter which direction you go. So boom, there, any direction the radius is the same. You're used to that since you were a tiny little kid. But ellipses here, they've got a different radius. If we go from the middle to an edge, that's all different lengths. So we're going to talk about the equations for these two types of things. And believe it or not, you've probably seen ellipses all over the place. It's just if you take any type of circle and you turn it a little bit sideways and look at it, you've got the form of an ellipse. Now, of course, that's not the only application, but I wanted you to see that you've probably seen them around quite a bit before. So the first thing is labeling our graph. I have two ellipses there on your notes, so we can take this first one and we're going to start labeling a bunch of things. So we have a vertex at each end. Together they're vertices, plural vertices. So label each end, the one that is farthest away from the center. So we have our center point and we're going the furthest away to get to a vertex. Then if we connect the vertices and go all the way across, that thing there is called the major axis. Then if we go the shorter distance away, it's called a covertex or covertices. So from the center to the closest point on the ellipse is a covertex. And if we connect them, we get the minor axis. So the major, it's majorly longer than the minor, which is smaller. Major axis, minor axis. Major axis connects vertices. And then you have this thing you most likely have probably not seen before. Oh yeah, minor axis. And that is these things called a focus or foci. Their plural would be F-O-C-I, foci. Now we have this in parabolas, so they do have a little bit of some similar things going on. But these little dots right here each of them are called a focus. Now what they actually do is just the kind of the cool thing. You don't have to write this part down in your notes, but what they do is if you take any single point along the ellipse and you were to connect them anyway, if you connect this point and you connect that point and add those two distances up, then you could take any other point anywhere else along the ellipse. Like let's say we took that point right there. If you take that point, and again, you just take, what am I looking for, a line here, and you go straight to each focus, and you add these two up, these two distances added up are going to be the same as this distance and this distance added up. It's kind of a crazy thing in the way ellipses work. Okay, but let's get rid of those lines and dots there. These are all the points that we need to have labeled. Make sure you understand each of those. So each one of those is a focus. Now let's go to your other ellipse, the one that's going up and down, this vertical ellipse. We're going to label some more things here. So the vertex is A units from the center. From the middle of the ellipse to a vertex is A. And that means the major axis, the length of the major axis is going to be double A or 2A. Then you have the covertex. It is going to be B units away from the center. So label this B all the way to a covertex. So the shorter distance is B. And that also means that the minor axis is going to be 2B units long from end to end from each covertex. And then the focus, or the two foci, they are going to be C units. So you see here I've labeled a couple foci. The distance here to here is C units. So what we can create is draw a line from the focus to the center, draw a line from the center to one of the covertices, and then if you connect that, you can see here we have this triangle. I know I may be going fast, so just pause if you're not with me yet, because a lot of stuff to label. What's really cool about this triangle is that the hypotenuse here, the length of that hypotenuse is actually A, the distance from the center to a vertex. It's just kind of this cool property that ellipses have. So what we have is also, if we know the distance between the center and C and the center and B, we can use it with a Pythagorean theorem. We see you're used to this, a squared plus b squared equals c squared. That's what you're used to, but what we're actually doing is we're not using that one. We're using this, b squared plus c squared equals a squared. Why is it different? Because these are the legs. The B and the C are the legs in this instance, and the A is the hypotenuse. So you just got to be careful how you write this down. We'll come back to this one. You could write this down somewhere near the ellipse, but we will have this also later in the notes. Cool little application thing with ellipses. I don't know if you've ever seen this before, but you could stand in a room that is an elliptical formed room, and if you talk straight watch this, if you talk straight at the wall at any area, it's going to bounce off the wall and go back to the other focus. So if you have two people standing at two foci, you can actually whisper towards the wall and phew, it bounces off. I've actually been in buildings like this before. It's really cool. Here's a little TV clip that actually shows. Okay, that'd be actually pretty funny if you could be in a room whispering and nobody knew where that voice was coming from. Standard equation of an ellipse. First part you need to make sure you get down is this. A is greater than B. Incredibly important. A is greater than B. You got to have that down. So wherever the A is on these, you'll always know that the larger number is going to be your A squared. This looks like a lot. It's not going to be too difficult. You'll see as we get through into the practice. If we have a horizontal ellipse, meaning that our ellipse is stretched out to the left and to the right, something like that, an ellipse that's going left and right, horizontal, then that means that our larger number is underneath the x. The way I remember this is that the x values go left and right, so if a is under x, the ellipse is going left and right. If the larger number a squared is underneath the y, then it is a vertical ellipse, so it's going up and down like this. So y values go up and down, so it is a vertical ellipse up and down. That's the way I remember this. It always equals 1 though. Okay, it's a big thing for an ellipse. So what do these numbers mean? This a and b, that if you remember, a is how you know from the center how far to go out for your vertex. And the b is going to be how far you go out for your covertex. So that'll help us with graphing, but there'll also be some applications in our word problems here. The center is at HK, so that's the same as we've been doing all year long. Our H and our K is going to be our center point. The foci are C units away from the center on the major axis, so it's always along the major axis. So from the center, left and right on a horizontal or up and down on a vertical. But how do you get this? Important formula here. C squared equals A squared minus B squared. It's just a manipulation of the Pythagorean theorem. What I showed you up before, where we had B squared plus C squared. So we come back here, and there we go. We just manipulated it and solved for C. So this one here, C equals A squared minus B squared. So the way I remember this is for an ellipse, our equation is going to be addition, but the Pythagorean identity over here, the Pythagorean relationship, I should say, that relationship is going to be subtraction for helping us find our C units. That's a big deal because in our next lesson, we'll do hyperbolas, which have a minus here, but it'll have a plus in the Pythagorean relationship. Okay, so again, ellipses are addition for the standard equation, subtraction for the Pythagorean relationship. In order to graph these and label all this stuff, we have to identify our A, our B, and our C. So what are those things? A squared is the larger number. So A squared is 9, which means A is just a 3. You take the square root. And then if this smaller number is the B squared, so if B squared is 4, then B is the square root of that, which is 2. How do we get our C? If you remember, it is equal to the square root of, remember our formula? A squared minus B squared. So it's the square root of 9 minus 4, which then is equal to the square root of 5. All right, so where is our center point? Let me switch colors here so we don't lose track. Our center point is going to be at -1, 3. It's from our coordinate point H and K. Remember, you always take the opposites. It equals 1, so we already knew this was an ellipse here. The vertices, well, that's actually, I think it's easier if we graph it. So -1, 3. Why don't we graph this first and then be able to figure out these vertices and co-vertices and all that stuff. So then, let's see, this is, the A squared is under the X, so this is a horizontal ellipse. I like to draw a quick little sketch to remind myself it's left and right. So from the center, I go out A units. A is a 3. I go 1, 2, 3. There's a vertex. From the center, I go 1, 2, 3 to the right. There's another vertex. Now, how far up and down do I go on this? I'm going B units. So 1, 2, put a vertex. And then from the center, 1, 2, there's a distance of B. There is our ellipse. It's almost a circle, but not quite. So to help sketch the graph of this, when I do these, don't make it like a diamond. You don't want to go like that. That is a horrible ellipse, so please don't do that. Try to curve it by just kind of coming straight up and down. That's how I make this look nice and curved. Kind of come out and then start eventually curving it. There we go. Oh, that was not as quite as nice as I liked, but it's close. Lopsided egg is what that looks like. Okay, vertices. So now we can label the vertices for our coordinate points. This one was at negative 4, 3. Negative 4, 3. And the other one was at 2, comma 3. So there's our two vertices. The co-vertices are the ones that are the closest to the center. So that coordinate point here is negative 1, 1. So negative 1, comma 1. And the other coordinate point was a negative 1, 5. Negative 1, comma 5. Okay, now for the hard part, the foci. Where are the foci? Let me use a blue dot here. We are square root of 5 away. Well, that's approximately 2 point something. I'm going to estimate it's probably about 2.1, 2.2, somewhere in there. So we're going to go from the center, 1, 2, and a little bit. And then from the center, I'm going to go along the major axis. That's why I'm going left and right. 1, 2, and a little bit. So where are the foci? From the center, switch back to my red. From the center, which was negative 1, we're going to add and subtract the square root of 5 from the center. And then what's the y value? It is a 3. So this right here represents two different coordinate points. The x values of negative 1 plus square root of 5 and negative 1 minus square root of 5, and then the y value is a 3. So there's all of our coordinate points, and there's your graph. Number 2, you're going to try it on your own, but we first have to help you set up a little bit here, and that is it must equal 1 before you can figure out all the a, b, and c stuff. So that means whatever the other side is, you have to divide every term by that number to create a 1. So dividing by 1225 will equal 1, and that means over here we go 1225, and here we go 1225. Now, the problems I'm giving you are pretty nice cookie cutter problems. These are always going to reduce nice and neat. Okay, those things are reducing. This thing's going to reduce. That thing just becomes the number 1. So what is our new problem? It is going to be x minus 2 squared over, you can work this with a calculator, or you just trust me, it's going to end up as a 25 plus, and then here we get y plus 1. This fraction reduces, oops, that's a plus 1, quantity squared, and that is going to end up reducing to 49, and it equals 1. Okay, so now you'll label everything that you need, your A, B, and C, try and list that out, find, actually graph it then find all these points. So pause now and try it on your own. Here's our answer for number 2. You can check my answers here if you need to pause and take a look a little more. The only thing I would point out would just be that you had to recognize that this was a vertical ellipse, so I just drew a quick little sketch down here to remind myself it was up and down, so that way when I found the A, which was 7, I went from the center up 7 and down 7. And that also meant that my C value for my focus, for my two foci, it was up and down. So that meant I added and subtracted C to the center point of a y value of negative 1. Okay, so pause there if you don't understand what's going on there. See if you can get the rest of that written down. Number 3. Now we're going to come up with an equation given some information. So my strong recommendation, in fact, not even recommendation, it's almost a must on every single one of these. Draw yourself a quick little grid and sketch, I mean like really sketch, it's nothing fancy. 28, so I go, my vertices, go out to the vertices, 20, up here to 8, and then 0, 8. If those are the vertices, that means it's this type of an ellipse. It's horizontal. All you need is to find the vertices and you'll know which type of ellipse it is. Okay, so that means what? It means that when I get my x squared term, the a squared is going to be underneath the x because it's a left and right. All right, let's figure out the center first. So that's what we need to do when we're working through these. The center point is going to be right in the middle of the vertices, or right in the middle of the co-vertices. So remember how to find the midpoint from a couple last lesson? The midpoint of 20, 0 is like the average. The average of 20 and 0 is 10. And then the average of 8 and 8, well, that's just 8. Okay, that's easy. So there's our center point. Now what? We need to figure out A. The A value will be from the center to a vertex. So the 10/8. Now you could use the fancy distance formula, you know, distance equals square root of blah, blah, blah stuff. But These problems are going to be so basic and easy because they're on a horizontal or vertical line. How far is it from the center 10 to a vertex that's at 20? And the y values are the same. Well, that's easy. A is going to equal 10. From 10 to 20 or from 10 to 0. Let me write what the b value is. The b value is from a covertex to the center. So here, in this case, the 10s are the same. How far is it from 16 to 8 or from 0 to 8? Well, that's an 8. We do not need the c because all we're doing is coming up with the standard form equation. So our answer is something plus something else equals 1. That's always how these equations work. So let's take the center. We have x minus 10 quantity squared. Then we have the y value, y minus 8 quantity squared. Technically, it does not matter which one of these goes first because it is addition. So you could have the x first or the y first, doesn't matter. What's important is that the larger number, the a, is going to go underneath the x because it is a left and right. So we put here, what do we put in? This is 10 squared. So that is 100. And then this one is going to be our b squared. So it is 64. There's our answer. Here we go on to number 4. The thing that's a little bit different with this one is that we have the foci and we do not have the covertices. So this is going to help us find our value of c. So let's sketch real quick again. So where's my vertices? -5, 9, there's one vertex, and -5, -1, there's another vertex. So what kind of ellipse is this? It is vertical because there's my vertices up and down above each other. So that means that it's going to have a y squared over the a squared with our fractions when we work through it. Okay, let's label everything that we can come up with. Center. Where's that? The center point is right in the middle of these things. So -5, -5, that's obvious, the average of those. So the center is at -5, comma. Then what's the midpoint of 9 and -1? Add them up. 9 plus -1 is 8. Divide that by 2, you get 4. So that's just finding the midpoint. What's next? Our A. From the center to a vertex, how far is that? -5 to -5 is nothing. 4 to 9, that value is 5. So our A is a 5. Our B, we won't know because there is no information for there to give us just the B. So let's, instead of writing down B, let's do this. Our formula is C equals the square root of A squared minus B squared. So sometimes it's nicer if you manipulate this. B squared equals A squared minus C squared. Okay, so let's go back. B squared equals A squared minus C squared. So B squared equals A squared, which is 25, minus C squared. What in the world is C? I should probably write that down. The C distance from a foci to the center point. You can see this 4 to the 7. That's a distance of 3. So that's 9 because it's C squared. So then B is equal to the square root of 25 minus 9 is 16. So it equals 4. All right, we have all the information we need. So the formula is we have a fraction plus another fraction equals the number 1. They're always set up like this. It doesn't matter which one we put first. It could be the x or the y, but I know, so I'll just put the x, and then I have the y quantity squared. And what is our center point? So plus 5 there, and then a minus 4 for the y value. Now it's just a matter of putting the a squared and b squared in the right spots. It's up and down, so the a value, 5 squared, goes under the y. So we put a 25 here, and not a 9, that was the c. Where's the b? B is a 4, so we put 4 squared under the x. Okay, there's number 4. And just as a reminder, if you don't draw this sketch real quick before you start coming up with the equations, you are most likely going to miss many of these problems and not pass that mastery check. So highlight of your notes, sketch the graph. Next up, we've got our circles. I know this lesson's long. Hang in there. We're at the easiest part of the lesson, circles. Now, circle is just a fancy way of doing an ellipse, really. I mean, if you think about it, It's just a special type of an ellipse where both the major and minor axis are exactly the same. So if you actually go right back up to your notes, way back on this part, maybe on the far left side of your notes, you could write if A equals B, see down here, instead of A being greater than B, if A equals B, then it's a circle. So you could still solve for 1, and if A and B are identical numbers, you have a circle because the major and minor axis are the same. So let's go back to this part of the notes. Okay, so standard equation of a circle. Notice that now this time it's not equaling 1. That's because if we had an A and B here that are the same, you just multiply both sides by that number, you get r squared. This is the standard form equation of a circle where you have a center at HK and the radius is r. So be careful here. If you have an 81 over there, the radius is not 81. The radius would be 9. So just remember that. You got to take the square root of these things. Now, circles are used everywhere, even in the gym. Here we got Mr. Brust. He's lifting these circles here, and I really appreciate whoever took this picture and posted it on Facebook. That is worth so much to me. So again, thank you so much. But you can see circles are all over the place. So let's take our first example for circles, number 5, and you see here our A and B are the same, so that we know it's a circle. So what you could do is just multiply both sides by 16, and we get x plus 1 quantity squared plus y minus 3 quantity squared equals, and then we get 16. So now what is the coordinate of the center point? Let's switch colors. Why? I don't know, because I can switch colors. Coordinate of the center is -1, 3. There's our center, and the radius is a 4. Not a 16, a 4. So then we go -1, 1, 2, 3. There's our center point, and the radius of 4. So 1, 2, 3, 4. Just count out 4, up, down, left, right, all those things. And then 1, 2, 3, 4. And once you have 4 points, 1, 2, 3, 4, you know, this is actually exactly how I paint circles on a softball field when I'm coaching softball. I just go 4 main areas like this, and then I curve it, and I connect my curve. I don't even use, I know I'm probably supposed to use some like pretty chalk or something. I'm not the chalk, some string or something like that and go around in a circle. But I found if I just measure it, get the 4 corners, it works. Okay, pause the video. Number 6, real simple. Do this one. Center, radius, sketch the graph. There's your circle for number 6. I bet I caught you here on the quantity squareds. Look, I put the x second. So you had to recognize that the center's at 1 here, 1, 2. So be very careful that the x value goes with the x. It's not just the number in front. And then I figured it was approximately 2.6. And look how awesome my circle is. I did cheat though. I used a tool to help me draw that. Okay, so there's number 6. Now we're going to come up with an equation, and all we have is this information. This isn't as bad as it looks. What we're going to do is think, what is the equation? So we have x minus 3 quantity squared plus, what's our y value? Y plus a 7 quantity squared equals, let's say radius squared, assuming we don't know what the radius is. We know a point on the circle is 1, 0, but let's say we don't know what the radius. All you have to do, yes, you could do the distance. You could do the distance formula between the center and a point on the circle, and that absolutely would work. It would give you the radius, and then you square it. But let me also point out that all you really have to do is take the point on the circle, 1, and plug it in there, and then you take the y value of the 0 and plug it into the y, and solve for r squared. So let's try that. So we'll take 1 minus 3 squared plus the 0 plus 7, right, squared equals r squared. So here you have -2 squared plus 7 squared equals, equals r squared. 4 plus 49 is 53. So 53 is equal to r squared. Now technically r is going to be the square root of 53, but all we're trying to do is write an equation. So our equation is, let's change color so it stands out, our equation is x minus 3 quantity squared plus, now we go to our y value, sloppy, y plus 7 quantity squared equals 53. And that is the equation for the for the given information. So we have our center point, and then 53 r squared is our r squared over here on the right. Why don't you now pause knowing how to do that? Try number 8 all on your own, and I'll have the answer appear in just a sec. There's your answer to number 8, x minus 5 quantity squared plus y squared equals 45. You can pause there and take a look if you want. That is officially the end of our lesson. Rock that mastery check. I'm not signing off yet, though, because I've got a cool little information to show you here these last few minutes. This would be a video I'd show in class if I was actually teaching traditionally. So this has got some cool stuff dealing with astronomy and ellipses. So you don't have to watch this. I know it's not part of the master checker lesson. It's just for those of you who want to be enlightened. So those of you who are lame and you don't care and you just want to get to the practice, so boring, go ahead. You can your lesson's over. But for those of you who want to just learn for learning's sake, stay with me. A German guy named Johannes Kepler. This guy lived a long time ago, 1571, 1630. And he discovered something cool, is that planets moved in an elliptical motion. So what happened was he was studying some measurements that this guy, the last name was Brahe, Tycho Brahe. He was studying some measurements this guy had made up in the sky, watching the planets go around, like Mars or something like that. He'd watch Mars go around and around, and he'd measure how long he thought it was taking to get around the sun. And so you have this circular motion, and Brahe said that it went around in a circle around the sun. Well, the problem is that Kepler discovered that this just didn't make sense. He would take these measurements and use some cool mathematics and figure out that it was off, just slightly, but it was getting more and more off with the more years that would go by based on his measurements. So he discovered that if he used the sun at one of a focus, and he created it as an ellipse, that the Mars was going around the sun in an elliptical format, it matched perfectly. So that's kind of a cool thing that he discovered. Here's a little video from this real famous astrophysicist. This is a while back. It's a little old. The guy I'm going to show you in the video, his name is Carl Sagan. Pretty famous guy from back in the 70s and 80s. So just kind of listen to some of his explanation, cool stuff that he shows here, and then I'll see you back in the next lesson.
The difference between a circular orbit and the true orbit of Mars could be distinguished only by precise measurement and by a courageous acceptance of the facts. Kepler was profoundly annoyed at having to abandon a circular orbit. It shook his faith in God as the maker of a perfect celestial geometry. Having cleaned the stable of astronomy of circles and spirals, he said, he was left with only a single cartful of dung. He tried various oval-like curves, calculated away, made some arithmetical mistakes, which caused him, in fact, to reject the correct answer, and months later, in some desperation, tried the formula for the first time for an ellipse. The ellipse matched the observations of Tycho beautifully. In such an orbit, the sun is not at the center, but is offset. It's at one focus of the ellipse. When a given planet is at the far point in its orbit from the sun, it goes more slowly. As it approaches the near point, it speeds up. Such motion is why we describe the planets as forever falling towards the sun, but never reaching it. Kepler's first law of planetary motion is simply this: a planet moves in an ellipse with the sun at one focus. As the planet moves along its orbit, it sweeps out, in a given period of time, an imaginary wedge-shaped area. When the planet is far from the sun, the area is long and thin. When the planet is close to the sun, the area is short and squat. Although the shapes of these wedges are different, Kepler found that their areas are exactly the same. This provided a precise mathematical description of how a planet changes its speed in relation to its distance from the sun. Now, for the first time, astronomers could predict exactly where a planet would be, in accordance with a simple and invariable law. Kepler's second law is this: a planet sweeps out equal areas in equal times. Kepler's first two laws of planetary motion may seem a little remote and abstract. All right, planets move in ellipses and they sweep out equal areas in equal times. So what? It's not as easy to grasp as circular motion. We might have a tendency to dismiss it, to say it's a mere mathematical tinkering, something removed from everyday life. But these are the laws our planet itself obeys as we, glued by gravity to the surface of the Earth, hurtle through space. We move in accord with laws of nature, which Kepler first discovered. When we send spacecraft to the planets, when we observe double stars, when we examine the motion of distant galaxies, we find that all over the universe, Kepler's laws are obeyed.